I'll do recording here. So let's take a look at some chapter 8 problems. I haven't done that yet, chapter 8 and chapter 9. So let's go back. We'll probably have to add some. Now, their classification scheme is a little different than mine. What we're going to do is we're going to classify it as redox, metathesis, acid base. And this one, magnesium plus nitrogen. Magnesium wants to lose 2, nitrogen wants to gain 3, you know. So, you know, losing and gaining electrons is oxidation. So I classify this as an oxidation, or you could classify it as a combination reaction that's oxidation, reduction, redox. And so my classification is this is redox. It's not redox decomposition, it's redox combination if you want, or just call it redox. And magnesium wants to lose 2, nitrogen wants to gain 3. And so we're going to end up forming Mg3 and 2. So magnesium nitride would be the name. Magnesium nitride. That's what we expect. And so nitrogen is being used as an oxidizer. Now nitrogen's not that great of an oxidizer, you know, especially when compared to oxygen. But you know, magnesium is a pretty good reducer. And so you don't have to be a very good oxidizer to react with magnesium. When oxygen reacts with magnesium, have you ever seen oxygen react with magnesium? Yeah, you have, but I don't know if you recall, what color is the flame? And so look at burning magnesium. You're not supposed to look at burning magnesium because it's like almost like sunlight, you know, it's so bright it emits some UV, which can damage your eyes. So you're not supposed to look at it directly. Let's take a look at some burning magnesium here. Okay, come on. I just want a short video. "28 seconds is short enough." So if we use oxygen, you know, to burn magnesium, then we're going to get a nice white flame. Can you guys see this? Yeah, should be seeing this. This is some chemistry club. Smoke is magnesium oxide. Or is that CO2? That might be CO2. They might be burning it in CO2. Once somebody was burning some magnesium at El Camino and set off the fire alarm, and the whole building had to be evacuated because of the magnesium oxide smoke that was triggering the fire alarm. That's with oxygen. With nitrogen, you're not going to get that kind of reaction. Nitrogen's a much weaker oxidizer. I don't want to close that. I need to. Okay. Wait a minute. Just 1 second. All right, sorry, I'm back. When we look at this next reaction, automatically I see AB plus CD. So zinc with sulfate. Zinc is a 2+, sulfate's a 2-, so 1 to 1's fine. And then hydrogen with hydroxide. Well, hydrogen hydroxide is just water. And that would be it. Now, this is often the case in your book. This is going to be aqueous. This is sulfuric acid, so this will be aqueous. Zinc sulfate. Sulfates are all soluble, except for silver, lead, mercury, calcium, strontium, barium. And so this is aqueous. This shows a liquid. So do we have driving force? We do have driving force. We're going from a stronger acid, H2SO4, to a weaker acid, H2O. That would be it. We need to balance this by adding 2 waters here, and then it's all balanced. So this would be the CE. The IE is, what we do is we, zinc hydroxide, sorry, zinc hydroxide aqueous. I have to think about my solubility rules. I think I made a mistake because all hydroxides are insoluble except for group 1, ammonium, calcium, strontium, barium. So I made a mistake. Zinc hydroxide is not aqueous. Zinc hydroxide is a solid. And so we're dissolving this solid in sulfuric acid, but the driving force is going from stronger acid to weaker acid. All we need is one driving force. And so let's go on to the, well, anyway, this is the CE. Let's go on to the IE here. And so the IE, we dissociate the strong electrolytes. Zinc hydroxide is an insoluble solid. So what we'll do is we'll just leave it alone. If it were soluble, then we'd break it apart. H2SO4 is a strong electrolyte. Now, H2SO4 is very tricky because H2SO4 is what we call a diprotic acid. Diprotic acid has 2 acidic hydrogens on there. But the tricky thing about this is both don't break off at the same time. Only one breaks off at a time. And so it's going to end up as H plus and HSO4-. However, when I did the double replacement, I treated it as sulfate, not bisulfate here. And so if you look at my product, I have both H's broken off. And that's what's going to happen in the double replacement. So double replacement will go to full reaction. And so the second hydrogen will come off, and that's going to form zinc sulfate. Well, zinc sulfate, that's a soluble salt. So that's going to break up into ions, zinc ions and sulfate ions. And then finally, H2O is not a strong electrolyte, so H2O liquid just stays alone. Are there any spectators here? It turns out there are no spectators here, so the ionic equation and the net ionic equation are the same thing. Same thing, so let's go on. Next reaction is zinc with iodine. Zinc with iodine, what kind of reaction is that? Well, the species on the right in the periodic table wants to take electrons. So iodine will take electrons, zinc will lose electrons. In other words, it's an oxidizer. Nitrogen up here is the oxidizer. Nitrogen is going to strip electrons off magnesium. Iodine's an oxidizer, you know? Iodine's a pretty decent oxidizer. Iodine's a much better oxidizer than nitrogen. Nitrogen, you know, nitrogen's, you know what they call nitrogen? They call nitrogen a pseudo-Nobel gas. It's a pseudo-Nobel gas because nitrogen's so unreactive. Nitrogen doesn't really oxidize anything, much of anything. So only under, you know, well, it can oxidize things like magnesium, which is a really powerful reducer, but it doesn't really oxidize much else. Iodine's much stronger. Iodine, each iodine wants 1 electron. Zinc is capable of losing 2, so I'll need 2 iodides. I expect to form Z and I2. There's no water around here, it looks like. You know, this looks solid. Iodine is solid. And so this is solid. Oh, combo. Lead 4 oxide is stable. Lead 4 oxide is a decent oxidizer because lead, what's the charge on lead in lead 4 oxide? That's +4. In case I miss this, move this over to the sides. And so if we were to heat this up or something to cause it to decompose, you could heat it up to cause it to decompose to possibly form something like lead metal and oxygen gas, O2 gas. Well, it happens to be balanced if we do this. So this is decomposition. Or it might form lead 2 oxide plus half an oxygen gas, you know, half a mole of oxygen gas, something like this. This would be balanced too. Or maybe other things, you know, but these seem reasonable. Lead 2 oxide or lead, you know, and oxygen is a decomposition reaction. I think that's what they're looking at. It's a redox. This is a redox reaction. You know, lead 4 is going to +2 or 0. Oxygen is going from -2 to 0. This redox. This here is single replacement, you know, A plus BX. Let me tell you right now, the single replacements work in the Chem 4 homework. They don't work in the Chem 1A homework all the time. So you could do this by a single replacement, or you could do this by a chart method, you know. We could do it by a chart method, because chart method is more powerful. So let's get more practice with chart method. So aluminum solid, and copper 2 sulfate is going to be an aqueous solution. Solid to solid reactions are very slow. Copper 2 sulfate pure is solid, but you know, you'd have to grind them together using a mortar and pestle or something. Let me take that back. Not all solid to solid reactions are slow. So be careful. Be careful. Inventory. Well, we're going to have aluminum metal. We're going to have, oh, copper 2 sulfate is a strong electrolyte, the soluble salt. So we're going to get copper 2 ions and sulfate ions. And we have water. Then we assign based on the chart. So aluminum is a reducing agent. It's on the lithium side. Copper 2 is an oxidizing agent. It's on the fluorine side. Sulfate, this one is a problem. Sulfate is an oxidizing agent, but it's missing H+. We need acid. There's no acid in our inventory. So what that means is its rank drops significantly. So for right now, we're going to ignore it because we need that H+. If we look at the chart, it's sulfate plus 8H+. And so we're missing that. It's the one thing is, it's like this. Let's say you need, let's say this is sugar. And let's say this is flour. And let's say you're making cookies. And so you need 1 cup of sugar and 8 cups of flour. Let's say you don't have any flour. So you're going to make cookies out of 1 cup of sugar. Well, are your cookies going to come out that great? You know, if you make them out of 100% sugar with no flour. No, you aren't going to be able to make them. And the same thing here. You know, if we're missing a key ingredient, then our recipe isn't going to work. And so H plus is a key ingredient, which we're missing. So that's why I put an asterisk here, and we have to treat that differently, even though it's on the chart. Water is going to be an oxidizer and a reducer. For right now, we're going to ignore this. In Chem 1B, you can figure out, you know, if we're missing acid, how much does rank drop? Is it still significant, you know? It's still an oxidizer. It's just going to be a heck of a lot less reactive. So that leaves copper 2 is the strongest oxidizer. And the strongest reducer is aluminum metal. Well, that's what we would have predicted using A plus BX. You know, A is the reducer, B is the oxidizer. We look at the chart. Aluminum solid goes to aluminum 3 plus 3 electrons. And copper 2 plus gains 2 electrons to go to copper solid. Now, this is mismatch in electrons. It's a mismatch, so the first reaction we're going to multiply by 2. That's going to give me 6 electrons. And the second reaction we're going to multiply by 3. That's going to give me 6 electrons. So 6 electrons, 6 electrons. We're set. And then I'm going to sum up everything on the reactant side. 2 aluminum solids plus 3 copper 2 plus 6 electrons. And then I'm going to sum up everything on the right side. This is going to yield 2 aluminum 3 plus 6 electrons plus 3 copper solids. And then I'm going to get rid of the spectators. 6 electrons, 6 electrons. That's it. And so the net reaction is 2 aluminum solids plus 3 copper 2 plus yields 2 aluminum 3 plus 3 copper solids. So what's happening here is the copper 2 ions are oxidizing the aluminum. This is a redox reaction. Redox. And each copper is taking 2 electrons, and each aluminum is losing 3. So this is redox or single replacement. If we did the single replacement and then got the net ionic, this would be the net ionic equation. You know, the chart method always yields the net ionic. Now, if copper 2 sulfate were solid, it would probably react a lot slower. But, you know, you can't always assume that. Sometimes solid-solid reactions can be fast, especially if they're heated. Like say aluminum doesn't, you know, the melting point of aluminum isn't that high. And so aluminum can melt. If we have molten aluminum, then there's a lot of mobility. You know, because in a solid, there's no translational mobility. And so, but if you can melt the aluminum, then there's translational mobility and you get reaction occur. And so let's take a look at this. This reaction reminds me of one reaction. This reaction reminds me of this. Let me clear. It's the reaction between solid aluminum and iron 3 oxide. Now, tell me, what do you expect to be a better oxidizer? Copper 2 or iron 3? Which one do you kind of expect to be a better oxidizer? Copper 2 or iron 3? What would your guess be? I don't know, my chat window was frozen, sorry. Okay, I missed some questions. Why do you multiply by 2 and 3? We multiplied by 2 and 3, Kazra, to make sure the electrons balance, you know. If one produces 3 electrons and the other needs 2 electrons. The electrons are mismatched, so we have to multiply it so that we have just the right amount. We can't, in other words, we have to, in these redox reactions, we always have to have the electrons cancel in the full reaction. In the half reactions, we don't. The half reactions are only the 1/2 of it, you know, the whole reaction. So aluminum can go to aluminum 3+ plus 3 electrons, but those 3 electrons just can't sit. You know, you can't just put those electrons in a bottle and save them on the shelf for later, you know. And so those electrons have to be taken. They have to be taken by something. They're taken by copper, but copper doesn't want 3 electrons. Copper wants 2 electrons. Well, then go with 2 coppers. But if you go with 2 coppers, then 2 coppers want 4 electrons. And then aluminum doesn't supply 4. Aluminum only supplies us 3. And so bump up the aluminum, go to 2 aluminums. Well, if you go to 2 aluminums, we get 6 electrons. And 2 coppers don't want 6 electrons. 2 coppers want 4 electrons. So bump up the coppers. So you go to 3 coppers. When you have 3 coppers, then 3 coppers want 6 electrons. 2 aluminums want to give up 6 electrons, and everything works out, and it's a happy ending. So that's what redox always has to have, that happy ending, in which everything is perfectly balanced. That's why we do that. Now, iron should be a better oxidizer. Why? Because it's charged. Look at the charge, +3 versus +2. Size also has an issue, you know, and so we don't know for certain because of the size might dictate copper if iron's quite big, but both of these are quite small. And so iron 3 should be a better oxidizer. So this should be a more vigorous reaction here. In fact, they give this reaction a name. The name of this reaction, aluminum with solid, this is rust. And so aluminum metal with rust is called thermite. It's a, what kind of reaction? It's a redox reaction, right? Rust is our oxidizer, aluminum is a reducer. Let's check out this video here. Do I have audio? Wow, why is the resolution so bad? This is not looking good. It's really bad resolution. Let me see if I have a better one.
We have received
240.
letters and emails about thermal.
People keep uploading videos and the old good ones are gone.
I've got another request here. It's from Jordan Baxter, age 10, of Somerset.
Try putting a watch of thermite the size of a dinner plate on a car bonnet and see if it burns into the ground.
Okay.
All right. Well, anyway, we're going to try watching this one. So let me back it up. Turn up the volume.
From the sheer volume of emails we receive every week, it is clear that you are obsessed with thermite, the fiery substance that's hotter than a blaze in a chili factory. I've got another of your requests here. It's from Jordan Baxter, age 10, of Somerset.
Try putting a wad of thermite the size of a dinner plate on a car bonnet and see if it burns into the ground.
Okay. This is thermite. It's a powdered mixture of iron oxide and aluminium, which, when ignited, burns at 2,500 degrees Celsius, which is very, very hot. This is a car. It's been specially chosen to be destroyed because it's old, it's white, but more importantly, because it's French. The engine block is the densest part of the car. It's basically a huge lump of metal, and, well, it's very hard to melt. Lucky then, the brainiacs have plenty of thermite, specially packed into the slow-release mechanism of a garden flower pot. A big pile on the bonnet directly over the engine block should do the trick. Time to light the fuse and give this homage to French engineering the send-off it so richly deserves. The irreversible thermite reaction begins. Within seconds, the fiery concoction eats through the bonnet, spraying molten thermite into the engine beneath. The devastation continues inside until finally a torrent of white-hot liquid metal pours out of the bottom, signaling the inevitable victory for thermite. A quick check confirms a clear path of destruction through the engine. So, there you go, Jordan. Thanks to thermite, this car's driving days are well and truly over. We have received hundreds of your letters and emails about thermite, the substance that's hotter than an oven full of lava. Every week, you send us a whole batch of new ideas. And this week, we've got a little gem, courtesy of Ryan Tucker, age 34, from Sidcup.
Dear Brainiac, will a car explode if you start a thermite reaction on top of it and let it burn through to a full petrol tank?
Oh, I don't know, but I've got just the car for it, so let's find out. This is thermite. It's a powdered mixture of iron oxide and aluminium, which burns at 2,500 degrees Celsius, which is very, very hot. This is a car, or at least it was until last week when it got its first taste of the awesome power of thermite. Now that the engine is melting clean through, it seems only fitting to have a go at the petrol tank. Packed into the slow-release mechanism of a garden flower pot, the thermite is ready for action. Popped onto the roof, directly above the fuel tank, top up, and just 4 feet of family car stands between the thermite and 8 gallons of petrol. Light the touch paper and stand well back. The irreversible thermite reaction begins. Thermite produces a stream of molten iron which melts through the car in seconds. It's 2,500 degree heat igniting the expanding petrol in a devastating fireball, leaving behind a car that won't be going very far anytime soon. So there you go, Ryan. Can thermite make a car explode? Never yet.
Okay, so that was thermite. Thermite, we could do single replacement. Thermite's a single replacement, or you would use the CHARP method either. We'll take a look at the reaction for thermite right now. So we have aluminum, solid, they use powdered aluminum. Powdered aluminum is going to react a lot faster than really big chunks of aluminum. And they use powdered rust, like this. Now solids don't react very quickly. So they use some touch paper to get things hot. When things get hot, then there's a lot more kinetic energy, and reaction can occur there. So what we're going to do is we're going to set this up as single replacement. So that's going to make aluminum oxide. Now aluminum loses 3, oxygen gains 2. So aluminum oxide is going to be Al2O3. And we're going to form iron metal, plus iron metal. Now, normally iron is a solid, but the temperatures, this is so exothermic. That is, there's so much energy produced in this. They need a little bit of energy to start it. That's what the touch paper was for. But once it gets started, then it's self-sustaining because lots of energy is produced in this highly exothermic reaction. So much energy is produced, it melts this stuff, the iron. So the molten iron melted through the car, basically. And this is aluminum oxide solid. So we're going from more active aluminum to less active iron. You might think that, hey, wait a minute, you know, isn't iron more active? Iron rusts. Aluminum, there's lots of aluminum things. Well, aluminum gets oxidized very rapidly. Aluminum gets oxidized more rapidly than iron. But the oxide coating of aluminum, this stuff, is incredibly tough. This oxide coating provides a surface layer protector. It's like, you know, when we buy those glass screen protectors for your phone, you know, this provides that extra layer of protection. Rust should do the same thing, except rust is crumbly, you know, brittle. Aluminum oxide is compact and very strong and impermeable. So this is called anodizing. When you anodize the surface of aluminum, it provides a tough oxide layer. If you try to anodize the surface of iron, it forms a very porous, crumbly, rusty layer, which falls off. This stuff doesn't fall off. So this protects the underlying aluminum. It's like copper pennies, you know, they got that black coating on it. Underneath is copper. Okay, so this is the this is it. Since all these are solids, you know, because we'd wait, the iron would eventually cool down to room temperature and become a solid again. We aren't going to have an ionic equation or a net ionic equation for that. So that's that. This would be a double replacement reaction. So let's quickly AB plus CD. This is going to give us iron. What's that? Iron 2. This is going to give us iron 2 phosphate. Now, iron is 2 plus, phosphate is 3 minus. And so we need 3 irons to balance it out and 2 phosphates. And then sodium and chloride. Well, sodium and chloride are NaCl. Is there a driving force? Yeah, phosphates. You know, phosphates are insoluble. So it's going to be a precipitate, except for group 1 and ammonium. This is not a group 1 or ammonium. So phosphates. So we call this a precipitate. Well, let's make sure. Well, chlorides, bromides, and iodides are soluble except for silver, lead, mercury. So this is aqueous. And sodium salts are aqueous. And so this would be called a precipitate here. And sodium chloride just would be aqueous, you know, soluble. Now we have to balance it. It looks like we're going to need 3 sodium chlorides to balance this. Actually more, because we need 3 irons here. So we need 3 iron. So that gives us 6. Sorry, so this is not 3. This is 6 sodium chlorides. So we get 3 iron, 6 chlorides. 3 iron, 6 chlorides. And over here we have 3 sodiums. Well, we need 6 sodiums, so I'll make that 2. So 6 sodiums and 2 phosphates. 6 sodiums, 2 phosphates. Now we're balanced. And so this precipitation is the driving force for this reaction here. All right. That's that. Okay, the next one is aluminum and HCl. We could do this chart, or we could do this single replacement. You know, single replacement is fine if it's a mineral acid. This is a mineral acid. If it's an oxidizing acid like nitric acid, perchloric acid, we probably shouldn't. And so if we use the A plus BX, the main advantage is it's fast. And so aluminum goes to aluminum 3 plus, chloride stays the same. So this will be AlCl3, aluminum chloride, and then hydrogen gas, H2 gas. And then compare aluminum solid versus hydrogen gas. Which one is more active? That one I'd have to look at the chart because I gotta see. Well, here's aluminum right here, and then hydrogen gas is up here. So aluminum is more active than hydrogen gas. Hydrogen gas is less active. So let's go back. Here. And so aluminum is more active, hydrogen gas is less active. So we're going from more active to less active. In other words, we're going from a stronger reducing agent, you know, activity series is reducing agent. So we're going from stronger reducing agent, aluminum, to weaker reducing agent, hydrogen, like that. And so that would be single replacement there. Replacement. All right, let's see. Okay, why don't you guys, I'm gonna, I kind of gave you an idea, you know, doing some examples to start. Why don't you guys finish these here? I'm gonna break you up into rooms if you want to. If you have a preference for rooms, let me know. Oh, is it, it's not break time, is it? I don't think so. So work on these 8 through 12 in a breakout room. Okay, let me see how many rooms. We will do five rooms, 3 to 4 people. Okay. It's mostly 3. Let me redo that. Okay. If you want to move around, let me know, and then I can move you guys around. So go ahead and join the rooms and then work on these ones here. I want you to predict the product and the driving force. And tell me what type of reaction it is. Okay, does anybody want to move? All right, I'm going to make the rooms a little bit bigger. I'm going to move some people just to make it a little bit bigger. Otherwise, one room has too few people. So just evened out the rooms. Maybe they're too big. There are 5 people in each room. I'll try to make it more random in the future. Let me know if you have questions, you know, or I'll be joining some rooms shortly just to check on, you know, people. So work on those and I'll check in on you guys a little bit. Oops, did I forget to pause the recording? Let me see. Let me pause it. Okay, so it sounds like a lot of you got pretty far along or finished that. So let's take a quick look at those, and then we're going to continue here. Let's see. Share this. I think I'm stuck. Okay, here we go. Okay, get back here. Okay, let's do a quick check here. So in an effort to save time, I'm just going to go through these quickly, and then we'll, if you have questions, stop me. But HGO, you know, this looks like a redox decomposition. And so I would just break it into the elements. So we're going to form liquid mercury and oxygen gas, O2 gas. And looking at this, we'll need 2 of these because we have no 2 here. So that's going to result in 2 liquid mercuries. Now, HGO is a solid, like most oxides are solids, like that. And so redox decomposition. Now, there's a driving force for this, but for these types of element plus element or compound goes to element, we aren't going to write the driving force. We're going to write the driving force for the others. But this would be, you know, stronger oxidizer to weaker oxidizer reducer. In the case of HGO, Hg2 plus is the oxidizer, O2 minus is the reducer. So Hg2 plus is a pretty strong oxidizer. And so Hg2 plus is going to pull the electrons off oxygen, leaving oxygen with no electrons. And then mercury is going to go from mercury 2 to mercury 0 in the process. And so this is what we call auto reaction. You know, one atom in this is taking electrons, the other atom in this compound is giving up electrons here. Okay, and oxygen's usually not a very good reducer, so mercury must be pretty strong to do this. Usually you need some temperature to do this. Here we have 2 choices because the 2 choices are iron likes to form iron 2 or iron likes to form iron 3. And so if iron goes to iron 2, then oxygen likes to go to O2 minus. This likes to go to O2 minus. So the 2 potential products here are FeO, solid, or Fe2O3, solid. Now, normally when we have a choice like that, it makes things complicated. So oftentimes we'll just go to the max. You know, the max usually is iron 3. This is ferric oxide, this is ferrous oxide here. Iron 4, iron 5, iron 6, those are all very uncommon charges for iron. When I was a student at UCLA, I tried to make an iron 4 compound. And I think I was successful, but unfortunately, I had some problems with the container for that. I had to use something more powerful than oxygen. This is when I was in fluorine chemistry. So I used fluorine to try to get iron 4, but you know, iron 4 has only been made once, or so they claim it's been made once when I was doing that project. So I was just trying to repeat somebody else's work. Okay, looking at this here, this is an AB plus CD. AB plus CD is metathesis. We're just switching around the ions to see if they like each other better. Right now, iron's paired with sulfate. You know, there's iron 3. But would it be better paired with hydroxide? You know, and so the products here would be, okay, we got iron 3, which would be our A paired with D, hydroxide. And so what we're going to form here is one potential product is iron 3 hydroxide, like that. And then we have barium ions paired with sulfate. So this is metathesis. Metathesis are, you know, ion combinations. Now, it doesn't have to be an AB plus CD pattern to be metathesis. You know, for example, we could have iron. What ions does iron like? Iron likes lots of ions. For example, it loves phosphate. It loves carbonate. It loves hydroxide. It loves a bunch. It loves chromate. You know, it loves a bunch of these ions. How do you know? Because iron 3 hydroxide is insoluble. It precipitates. Hydroxides are all insoluble except for group 1, ammonium, calcium, strontium, barium. So this is an insoluble solid. So that means iron loves hydroxide, loves it enough to come together to precipitate. And then barium ions, we have Ba2+. Now we're going to try to pair them with sulfate. Is that a good combination, barium sulfate? And we think about sulfate. Now sulfate, in a lot of these double replacements, we look for three types of things. We look for precipitation. Well, we got one there. We look for stronger acid to weaker acid. We don't have that. You know, neither of these are acids. And we look for gas formation. Well, that's not a gas. This is not a gas. So we're looking for precipitation here. Now, sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. Oh, this is barium. So that's insoluble. So we have a double precipitation here. Double precipitation's a mess because, you know, the two precipitates are all mixed together. So it's hard to separate. So when you get double precipitation like that, we get both precipitates precipitating. You get this rust-colored iron 3 hydroxide precipitating on with white barium sulfate. And we end up with a solid-solid mixture. But nonetheless, this is a good driving force. So this is aqueous, this is aqueous. Now, for full practice, this is what we call the CE. And the driving force is this double precipitation here. So we got driving force is precipitation here. Just one second. Let me take care of something. Okay, I'm back. Sorry. All right, now this is the CE, or the complete equation. Now the ionic equation, we ionize the strong electrolytes. The iron 3 sulfate is a soluble salt, and so that becomes ionized into 2 iron 3s and 3 sulfates. So we got to just make sure it's balanced in the correct ratio here. 2 iron 3s and 3 sulfates. This is not correctly balanced here. So let me try that again. Plus 3 sulfates like that. Now barium hydroxide, hydroxides are all insoluble except for silver. Oh no, barium hydroxides are all insoluble except for group 1, ammonium, calcium, strontium, barium. So barium hydroxide is soluble. It's a soluble salt. It's a strong base also. There's a strong base that's also a soluble salt. So it's a soluble salt, so it's going to dissociate into Ba2 plus 2 hydroxides. Neither of these are soluble, so these stay the same, this one and this one. And then there are no spectators. So the ionic equation is the same as the net ion equation because nothing cancels out. These are favorable ion combinations. Iron loves sulfate, barium likes hydroxide. Or no, sorry, no. Iron loves hydroxide, barium loves sulfate. Those are better combinations than the existing combinations. That's called metathesis or double replacement. And the reason I don't call it double replacement is because you get caught up in this thing. It has to fit the AB plus CD pattern. No, it doesn't have to fit that pattern. You could have a whole bunch of ions. So for example, if I threw this on a test, let's say if I throw sodium nitrate, you know, plus silver acetate, plus potassium chloride, this throws people off. It throws people off because all of a sudden they say, okay, what the heck is going on here? You know, but this is just metathesis. We got a bunch of ions and then we try all the combinations of the ions to see which ions are the best combination. And once we do that, you know, for me, I see it right away. Silver ions love chloride ions. And so silver ions and chloride ions will precipitate out silver chloride. And then I see none of the ions, other ions like each other in particular. So, you know, it doesn't matter how many, I could put in 30 different chemicals in here and you just pick out the best ion combinations. That's why I call it metathesis and I don't call it double replacement. Of course, the book is going to call it double replacement because they're trying to limit DR for double replacement. They're trying to limit the number of patterns. This is the same thing, you know, this is acid base or double replacement. And so in this reaction, I would just look at it as an AB plus CD. I mean, if it's double replacement, might as well use that pattern because it's pretty simple. And so we have H plus being paired with hydroxide. Well, that's a good ion combination. When H plus is paired with hydroxide, it forms very stable water. And then we have cesium plus paired with nitrate. Well, maybe that's not so great because cesium and nitrate, that does not precipitate, that does not form a gas, and that's not a weaker acid from a stronger acid. So, but it's okay, we'll leave it because water is good here. And so nitric acid is aqueous, cesium hydroxide, all group 1 salts are aqueous. That's aqueous. H2O is a liquid. Cesium salts are all aqueous, group 1 salts. And so what's the driving force for this? Well, the driving force is we got a stronger acid, nitric acid, going to a weaker acid, water. And so the driving force for this is stronger acid to weaker acid here in this double replacement. Okay, this is our CE, or the complete equation. The next step is to do the IE. Nitric acid is group 1, or strong acid, and strong acid, that's going to dissociate. And so the IE is going to have H plus and nitrate. This is balanced, by the way, so it's already balanced, so I don't have to do anything. Cesium hydroxide, you know, this is a soluble salt, group 1 salt, or a strong base. And so we're going to have cesium plus and hydroxide minus. Okay. And then water is not a strong acid, not a strong base, not a soluble salt. And then cesium nitrate, oh, that's a soluble salt. That's going to form cesium and nitrate here. Okay, let's look for the spectators. Well, it looks like nitrate's a spectator and cesium is a spectator. And so what we're going to end up with here is H plus hydroxide yields H2O liquid as our NIE, because the nitrate nothing happens to, and the cesium nothing happens to. And so this is our net ionic equation here. Okay. Could this be classified into 2 categories, double replacement or acid base? And actually, it's, you know, it's both, basically. Okay, this one is not double replacement. This could be a single replacement one here. But we have nitrate there. And so I need to talk about something here really quick. When we have nitrate, you have to watch out, right? When we have nitrate, X is no longer a spectator. Like for example, if we have A plus BX, you know, we want X to be a spectator. Well, nitrate doesn't like being a spectator because nitrate is quite reactive. And so this is something we have to watch out for. We need the chart method. Actually, once you do enough of these, then you'll see it's okay if we did single replacement for this one. But if we do the chart method, we have copper metal, and then silver nitrate. Nitrate, it's our soluble salts. Soluble salts are strong electrolytes, so we're going to have silver ions and nitrate ions. And then we're going to have water, H2O liquid. And then we look at our chart. You know, copper is on the lithium side, so that's a reducing agent. Silver is on the fluorine side, that's an oxidizing agent. Nitrate is on the fluorine side, that's an oxidizing agent. And water is on both sides, so it's an oxidizing agent, reducing agent. Then we have 3 oxidizing agents to choose from. We have silver, nitrate, and water. Which of those is the strongest? Silver, nitrate, or water? Which oxidizing agent is the strongest? Excuse me. Meneses, nitrate. Anybody else? Well, let's take a look at the chart here and see. If you say maybe, no, you should try to be a little more strong in your conviction. You know, So I see nitrate here, and I see silver here. So which one's stronger, nitrate or silver? Yeah, according to the chart, it's nitrate, but Moniz was correct to be apprehensive. You're correct to be apprehensive because of the H plus here. Nitrate needs H plus. H plus is a key ingredient. So for every nitrate, we need 4 H pluses. And so nitrate's like the sugar. Can we make cookies with no flour? H plus would be like the flour. And the answer is no, not really, at least not well. And so the situation with this is this. Even though nitrate, yes, we expect nitrate to be a powerful. We expect nitrate to be a powerful oxidizer. It's not. I'm going to write the little asterisk here. And the little asterisk is it's missing a key ingredient. We're missing the H plus. Do you see H plus anywhere in the inventory? If there was H plus in the inventory, then we're set. But there's no H plus in the inventory. And so it's missing H plus. Therefore, we're going to lower its ranking. In other words, we're going to ignore it as an oxidizer. If there was H plus present, then we'd factor it in because it'd be pretty strong. But without the H plus, it weakens it considerably. And like I said before, in Chem 1B, you can figure it out, you know, how much it's weakened, but Chem 4, we aren't going to go there. And so now that's going to leave silver ions as the oxidizer. And then the strongest reducer is copper or water. Well, the strongest reducer is going to be copper. And so let's look at the half reactions here. If copper solid is the reducer, then copper solid goes to copper 2 plus 2 electrons. And then if silver ions are the oxidizer, then silver ions gain an electron to form silver metal. And so it's a little bit mismatched here, you know. And so what we're going to do is we're going to multiply the second one by 2. And therefore I produce 2 electrons, I consume 2 electrons in this, and then add up everything. So take these and add it up. So we're going to copper solid plus 2 silver ions plus 2 electrons. This is going to yield copper 2 ions plus 2 electrons plus silver metal, 2 silver metals. Like that. And so the 2 electrons cancel out the 2 electrons. Now we have to look for a driving force. So when we look for the driving force, copper versus silver, you know, if we use metathesis, or we do it our regular way. Silver is our reducing agent. Copper is our reducing agent. Silver is our oxidizing agent. Copper 2 plus would be our oxidizing agent going reverse. You know, remember the conjugate relationships. If this is reducing agent, then its conjugate on the opposite side must be the oxidizing agent. If this is the oxidizing agent, then its conjugate on the opposite side must be the reducing agent. And so copper 2 is the oxidizing agent, silver is the reducing agent here. So then we compare what's a better oxidizer, copper 2 ions or silver? And so let's take a look at the chart again and compare. What's a better oxidizer, copper 2 or silver ions? So clear my drawing. Actually, don't clear. Let's clear just this. Here. So looking at this, I see silver ions are here, and then copper 2 ions are here. So silver ions are stronger. This is a stronger OA. This is a weaker OA. Okay, are we going uphill or are we going downhill? So let's go back to the reaction and see. So we're going from copper metal to silver, silver ions to copper 2. And so the problem here is this. We're going from weaker OA to stronger. Let's see, what did I say, copper? So we're going from stronger OA, silver ions, to weaker OA, copper 2 ions. And so let's look at the metals, copper versus silver. Copper versus silver. Let me clear this, it's getting messed up. And so when we look at copper, copper is a stronger Ra than silver. Copper is closer to lithium at the bottom. The copper is a stronger Ra than silver. And so this is the reaction I have so far. Just put it in, this is copper solid. This is my Ra. Actually, let's just write it over here. Copper solid plus 2 silver ions yields copper solid plus, copper 2 plus 2 silver solids. So here, as far as RAs go, this is a stronger RA. This is a weaker RA. This is a stronger OA. This is a weaker OA. And so, you know, I think I was wrong. You know, no driving force. There is a driving force. What's a more stable metal? You know, if you're going to have jewelry made, would you want the jewelry made out of copper or would you want the jewelry made out of silver? What do you think would last longer? Copper or silver? Silver. And so this turns out to be a driving force. We're going from less stable copper, which is a stronger reducing agent, to more stable silver, which is a weaker reducing agent. And so this is the driving force. That is stronger RA to weaker RA, stronger OA to weaker OA. And so we have that driving force there. So actually, sorry, I was wrong. There's a reaction here. Now I did this via the chart method. If we do this via the chart method, then this is the NIE. I could also use the single replacement method. If I use single replacement, then I would have gotten the CE. And if I got the CE, then I have to get the IE and the NIE in addition to that. You could have used single replacement for this particular one as well. Okay. We're just going to quickly look at these. I don't know if I'm going to balance it, but we'll look. This is element plus element. You know, sodium loses 1, so oxygen gains 2. So the correct formula is Na2O, sodium oxide. Okay. Sodium is a solid, O2 is a gas, Na2O is a solid. This is hydrogen and chlorine yields HCl. And so actually we could balance these two pretty quickly. You know, here. All these are gases. This is another redox reaction. Phosphorus and oxygen. This is forming phosphorus 3. You know, phosphorus 3 plus. But it could have gone to phosphorus 5 plus as well. 3 and 5 are common for phosphorus. But they're telling us what it formed anyway. KCl4. This is potassium perchlorate. In this case, the decomposition is not to the elements. You know, we had decomposition. What was it? Decomposition. Well, we had decomposition on the previous. Here's a decomposition. When we look at these decompositions, they aren't going to the elements. So what do they go to? How do you know? You know, they might go to the elements. Like we saw earlier, but we look for other species. You know, it might be in steps and that kind of stuff. But here we have KClO4, so you know it might form potassium metal plus chlorine gas plus oxygen gas. In this case, it just formed a compound plus an element here. What types of compounds? Well, we look for stable compounds like KCl. You know, KCl is very stable. And then O2 we've seen before. And so this is also an example of kind of the skeleton type thing. You just try different conditions. So, you know, when we look at, like, for example, nitroglycerin, you know, nitroglycerin decomposition. Nitroglycerin decomposes explosively, but it depends on the conditions for that. And so in this case, it's going to form decomposition nitroglycerin, which is carbon, hydrogen, nitrogen, and oxygen, produces carbon dioxide. And so the carbon and the oxygens can combine. Nitrogen N2, water, hydrogen is oxygen, and oxygen gas, you know, under certain conditions. Under other conditions, it can form other products which are potential. But we look for things that are stable, like potassium chloride stable, you know, water stable, those types of things. And so this one might have been tricky here, you know, KCl, potassium chloride is pretty stable salt. Here, this is another decomposition. Oh no, this is double replacement, AB plus CD. This is antimony 3. So it formed antimony 3 with chlorides. This is H plus with sulfide. H plus with sulfide is going to form H2S, hydrogen sulfide. Then that's double replacement. This one is tricky. You know, this one can be acid base or double replacement as well. And so let's see, what time is it? Try number 6 out. We don't really have time to break into rooms right now, but try number 6 out and see what you get. Now, number 6 can be done in 2 ways. Let me just write it down here. Number 6 could be done, I would do it, you know, metathesis, double replacement. DR for double replacement, or Bronsted acid base. So those are two things, but I'd try it with the metathesis double replacement. See what we get. This is aqueous. This is aqueous. If they didn't give us the products, could you figure out the products yourself? And so give that a try, and I'll give you a few minutes to do that, or a little more than a few minutes. I'll be back. Let me pause the video. We had talked about using aqueous ammonia the other day, just seeing if you remember what we do with aqueous ammonia. When we have aqueous ammonia, we do ammonia plus water. Remember, ammonia is a weak base and it hydrolyzes water to produce a little of the ammonium hydroxide. You can't buy ammonium hydroxide, so we always leave it as ammonia and water. Ammonium hydroxide is, you know, acid and base unstable, like, you know, like ammonium nitrate, you know, reducer and oxidizer, it's unstable. But ammonium hydroxide rapidly decomposes into ammonia and water. And then H2SO4 here. And so what we have is we have AB, which is ammonium hydroxide, plus CD, which is H and SO4. And so we'll try the ammonium ions with sulfate ions. And so ammonium ions with sulfate ions are going to form ammonium sulfate, like that. Because ammonium is a +1, sulfate's a -2. And then hydrogen ions with hydroxide ions. Well, hydrogen ions and hydroxide ions is just H2O liquid. Now we need 2 ammoniums. We only have 1 ammonium here. And so in order to get 2 ammonium hydroxides, we're going to need 2 ammonias and 2 waters, like that. And so 2 ammonias, 2 waters plus H2SO4 yields ammonium sulfate and water. Now, what's the driving force for this? The driving force for this is going from a stronger acid, sulfuric acid, to water, which is a weaker acid. And so in this case, stronger acid to weaker acid. Water is not always the weaker acid, but in a lot of acid-base reactions it is. And so this is driving force for this particular reaction. Now, the next step is to, this is the CE. The next step is to get the IE. So let me finish off with the IE and the NIE. Ammonia we leave alone. It's aqueous. Now the water, the weird thing is the water, look, I have two waters here. And I have, actually, is that one water? No, that's going to form two waters here. Because I'm going to end up with two hydroxides. If I end up with two hydroxides and two H plus, then I'm going to form two waters. And the two waters cancel out the two waters. So I got ammonia. So actually the CEs, I forgot to cancel out the water. So this is going to be the CE, H2SO4 aqueous, which is going to yield ammonium. All ammonium salts are soluble. So this is ammonium sulfate aqueous. And that's it. The water's canceled. Okay, this is my CE. And then let's do the NIE. Ammonia stays alone. Sulfuric acid is interesting because it breaks up in an H plus and an HSO4 minus. The second hydrogen kind of is stuck on there. And so you have to just remember that. And then ammonium sulfate breaks up into two ammoniums and one sulfate. And we look for spectators. Actually, there are no spectators here. Ammonia is not the same thing as ammonium, and bisulfate is not the same thing as sulfate. And so this is the IE and NIE here. Okay, so we're going to stop there. Those are number 6, and then we'll continue tomorrow looking at reactions, doing some stoichiometry problems, and then I have to talk about the next chapter, chapter 11, as well. Okay, any questions before we wrap it up? All right, thanks, guys. I'll see you tomorrow. Okay, wrap it up here. I stop recording. Oh,